Hello and welcome to the 6th lecture of Machine Learning for Robotics and Computer Vision. In this lecture we will talk about machine learning for computer vision tasks and will cover some methods to actually use the methods that we had described before for actual computer vision tasks. But first let's have a look at what happened in the last lecture. In the last lecture we talked about unsupervised learning, and here we covered several different tasks that we had, like the density estimation using a Gaussian mixture model, but also how we can reduce the number of features that we are using basically for our machine learning task in the end by using the principal component analysis. So here was the goal to reduce the number of dimensions. But we also looked at some visualization methods which allowed us to nicely visualize the structure of our data in a way that we can gain then some insights about the data. And here we covered the t-distributed stochastic neighbor weighting. But until now, we just covered different methods for doing machine learning. So we are covering the core methods of traditional machine learning, like in regression, like the linear regression, but also regression trees. But also for classification, the k-nearest neighbor, the naive Bayes, decision trees, logistic regression, random forest, and also some other ensemble methods like ADA boost and gradient boost trees. And finally then, as I said, some unsupervised methods. But until now, we just handled the feature vectors as d-dimensional vectors and never talked about what actually are these dimensions. In the beginning, I talked about that you can maybe gather this from some databases so that you have some features, something like housing prices or something like this. But for computer vision tasks, it's not so clear what is actually the feature. Is it the image itself, which is maybe not a very good idea because an image is just represented by RGB values for each pixels. So therefore, we are now looking here more on which features are used basically by these methods to actually do some interesting tasks. And for this, the specific term that often comes to mind is the term of feature engineering. So given an image, we usually want to have first extract some features and then use some classifier on top of this. So this is really a two-stage approach. We are first defining our features and apply on this classifier. So there are two separate stages in this approach. And then in the end, we want to have, maybe in a supervised learning approach, a label in the end. And most of the time, the task of the computer vision engineer applying machine learning approaches to images is basically coming up with some task-specific features. And this is what's called feature engineering. So the main task is to engineer some good features that represent, in the end, the thing that we want to have. But when we are talking about tasks for computer vision, then we are talking about different perception tasks. And here I'm focusing more on tasks that are also interesting for robotics. And these are mainly the perception tasks which deal with getting some insights about our environment. So when the robot is driving around, what can he see, where are objects located, and so on and so on. And the first task is, of course, the normal image classification. So we are getting an image and we want to assign some label to this image, so such that we are gaining some insight about where we are maybe, or what is basically represented in this image, such that we can use some insights about this. And in this example here, where I have this image of a street scene, it might be that we assign something like a label like there are cars, but it's maybe also a city environment, and we have in the front maybe a crosswalk that we want to reason about. And more specifically then, when we not only want to know in generally what happens in the image, we can also ask ourselves what each pixel belongs to. And this is the task of semantic segmentation. So here again we have an image, and now we want to classify not only the whole image itself in some categories, but classify each pixel. And in this case, we assign each pixel a specific label encoded here by these colors. And this might be something like here, this purple, like the road surface. but also the different cars that are encoded here with the blue colors. And in the back you see also a bus that is encoded by this dark purple color, and the buildings that are encoded by the yellowish color. So here we have specifically fine-grained classification answers in the end, so that we have a really fine-grained understanding of the environment. We can say something about, yeah, where's the drivable surface, which might be interesting for some applications like self-driving cars. But we also have an information about, okay, where are maybe pixels that are interesting for us in the environment. And but we don't have really an understanding about where are different objects located. And here comes the next task into play, where we have the object detection. Again, we have an image, and here we are now interested in finding the objects in the scene. And that means in this task that we are interested in finding bounding boxes that surround the objects in the scene. And for each object, we basically want to have one distinct bounding box. In this case here, we have these cars. Each car is surrounded by a bounding box, and then we have this bus in the background. So, and now the obvious next step is basically when we are basically have this, where we have a pixel-wise classification, and we have the bounding boxes, we can also combine them together. And this is a very recent task that came up, basically to combine both in a way that we have now not only pixel-wise labels for the classes, but also instance information. So instance information means that we are having really can distinguish different objects, so that in this semantic segmentation here, you cannot distinguish this pixel from this pixel, because they are just classified as car. So you have to do something in the end to figure out that there are different objects in the scene. And in the panoptic segmentation, this is nicely combined into one task, where we not only assign to each pixel a semantic label, like before in the semantic segmentation, but also for the so-called thing classes, which correspond to objects that we are interested in, a specific instance label. That means we can now distinguish between different cars, here indicated by the different colored outlines, and we can say something about the contents and the surfaces of the scene that we see. So something like the road surface here. And this is the panoptic segmentation. In this lecture, I specifically want to now focus on classification and object detection, because these are the classical tasks that were first solved by using machine learning in computer vision. And here specifically, we are now looking at the object detection. And here I want to talk a little bit about what is object detection. So in object detection, we are interested in having an image. That's the input. We have an RGB image, in this case here the street scene, which is extracted from the cityscapes dataset, showing Bonn basically. And in this case, we are interested in finding the cars. So that means we want to surround all the instances of cars by a bounding box. And the bounding box is now defined, can be defined differently. So there are common ways of defining the bounding box. And one very common way is to define the bounding box by the upper left corner. It's the XY coordinate, and by the width and the height. So this is everything that we need to define the bounding box. But we can also have just the center of the bounding box encoded, and the width and the height. So they are both equivalent representations, but from some advantages have the representations, and some disadvantages. But this is the thing that you will encounter here. And the last one, we can also define the bounding boxes by just the upper left and the lower right corner, like this here. So we have just 4 image coordinates in the end, which define then the bounding box in the image. But together with the bounding box, we are also interested in getting a score, which tells us how confident basically the detector is in the end, that the object that it found is really corresponding to the class that we want to have in the end. And in general object detection, we are not only interested maybe in cars, but we have many classes, and we want to localize all these classes in the object detector. The general approach of object detection is basically as follows. So to find the bounding boxes, we are just extracting regions from the image. And it maybe looks like this. So we extract this region, which corresponds to the bounding box surrounding this region. And then we are extracting features from this region and using then the classifier. And this classifier can be anything that we discussed before, like the logistic regression, but also maybe some more powerful methods like the adder boost to get the final classification result in the end. And in the probabilistic way, this would be then the confidences, then the probabilistic encoding that we had, like P of y given x. And this might be here for this car detector that we say like, okay, for this region, this classifier will then turn out to be saying like, it's very unlikely that this is a car. So it will return 0.1. And then we are extracting more regions from this scene, something like this. And hopefully, when the classifier is well trained, we extract features again. And with these features, then the classifier will then say something like 0.9, this is a car. And in the end, this is usually the last step, we only want to keep the high scoring regions because these are the objects that we are interested in. And how do we extract basically this region? And for this, the sliding window approach. We are just sliding basically the window, extract from each window a region. And for each of these regions, we are then applying our classifier. This is the standard approach of doing object detection. So we are just extracting densely regions over the whole image and then classify each of these regions. And the high scoring regions that we are then getting, so in this case here, this thing, we are just retaining in the end. And to get then differently sized bounding boxes in the end, we just have to rescale the image, then use the same sliding window approach, and then we are getting different scales of objects in the scene. And this is basically the approach that was followed basically in the traditional object detection approaches. So, but as you can see here, when we are applying the sliding window approach, then we will getting maybe many overlapping regions. So that might be when the detector is maybe very sure that this region contains a car, then it will maybe return 0.9, and then regions that are closely also containing some part of the car will also return something. But in the end, we are interested in finding the distinct objects in the scene. And that means in the end, we want to keep maybe the bounding boxes that are really on top of the object. And for this, the concept of non-maximum suppression comes into play. So in the end, we want to keep only high confidence detection, and we want to remove the non-maximum bounding boxes. So that means that we maybe keep this bounding box here, but we'll want to remove the bounding boxes that are overlapping with this maximum confident region, but are maybe not interesting for us because they are not right on the object. And for this, we have to talk about a little bit how large the overlap between the regions is. And for this, we have to define what is basically the overlap between two bounding boxes. And for this, we are talking about the intersection over union. And the intersection over union of two bounding boxes is very easy. So it's just the union of the both bounding boxes, so the region or the number of pixels that are basically covered by both of the bounding boxes, divided by the union of both bounding boxes. So, and this gives us a score that we can then use to reject bounding boxes in the end. And the non-maximum suppression now works as follows. We are sorting our boxes in the end by the confidence. And for each box, we are looking if this box is overlapping with some accepted bounding box from before with a larger threshold. And if this is the case, we are just dropping this bounding box because this is then not our maximum detection for this case. And for this, we have to define overlap score, and this is defined by the intersection over union. And usually something like 0.5 is then chosen because this will then give good results in the end. And it looks then something like this. So we have maybe the first region like this. which is directly on the car and is hopefully also a high confidence detection in the end. And because this is not overlapping with something, we are just keeping this bounding box. Then we are moving on. The next highest confidence detection is that's of course overlapping with the other detection, and therefore we are just dropping it. And when we go on, we are coming maybe to this. This is also a high confident detection, and it's not overlapping with something, so we are just keeping it. And then we are coming to this bounding box, which is again overlapping with an already accepted bounding box, so we are dropping this again. So when we move on, and then in the end we have the thing that we want to have. We are retaining only the maximum confident bounding boxes that also nicely enclose the objects that we want to have in the end. So in this case, the cars. So now you have an idea about how a general object detector works. So it extracts regions. For these regions, it extracts some features and then does the classification. And in the end, we are maybe throwing away non-maximum detections. But the question is now, how do we define these features that we are using? And for this, a seminal approach was the Viola-Jones object detector. So the Viola-Jones object detector in the beginning of 2000 was very highly regarded paper because it provided a good method for doing face detection in this case. So as you will see in the lecture, we are progressing from some specific tasks in detection to more general object detection tasks. And so because you have to start with something, and in the beginning, because there were not so many images available maybe, or there were no large data sets basically available, and the largest thing that you could think of is maybe having images with people inside there, and then you can do face detection on this. And for this face detection, the main building blocks for the Viola-Jones detector were the hair-like features, and then our approach that we already discussed, the adder boost that use these hair-like features. And for the hair-like features, they are just used the decision stump. So just a simple threshold on these features that is then doing the classification. And one integral part of this whole detection to make it really fast, because you have to remember we're having a sliding window approach, we're sliding over the image, doing a lot of classifications there, and to get it really fast, also on the computers of that time, to do a cascaded classification. So that means we are having increasingly complex classifiers, which is then rejecting early the really, where you can easily say that this is not containing a face in the end, and you don't have to worry about this so much. But now talking about the hair-like features, they're very simple, and this is also a very distinct property here, which can be efficiently used to really do the computation in a way that facilitates in the end also on these computers of the time real-time capable object detection. So the hair-like features are very simple, so they are always defined basically locally to the detection frame. So that means here we have our region from the sliding window approach, and for this region we are now evaluating something like this. So these are the hair-like features. So the features are just encoding the difference between all pixels, the intensity differences of all pixels in this white region minus all the pixels in the black region. And this is just giving us an idea about how the intensity changes between these two regions. And for these regions, Viola-Jones came up with specific patterns, so something like this horizontal, this vertical pattern, this horizontal pattern, but also this three-wise pattern where we maybe can encode lines or something in between, and this four pattern here in the end. And all the evaluations that you do in the end is just summing up all the values, intensity values of the white pixels minus the black pixel. And this is the thing that you take as feature input in the end in your AdaBoost approach. And you're not only doing this for the specific placements here, but for all placements. Basically, you can choose from all these different locations in the image the feature that is more or most likely to distinguish faces from non-faces. And for the AdaBoost approach, we are now using just the simple V classifier, which finds the best separation between the weighted positive and negative examples. You remember this from the AdaBoost lecture. So AdaBoost is weighting the examples, and using these weights, we are now finding the decision functions. So this encoded like this here, which is just checking if the difference that we find with the specific feature, so this Hj corresponds to a specific location in the detection window where we are evaluating our Haar feature, and just uses a threshold. And in this case, they also included this Pj, which is just -1 and 1. So this is an error, which just flips the sign here. And when this is true, then it returns 1, and when it's not true, it returns 0. So 1 corresponds here to phase, and 0 corresponds to not a phase in this case. And each stage of the AdaBoost training is now the best Haar feature selected, which separates the phases from the non-phases. And as you remember, AdaBoost is using the result of one of this stage-wise training to then find more Haar features in the end that distinguishes then the errors that it makes. And by doing this, you can then build a strong classifier in the end by just using these simple Haar features and this simple decision stumps in the end. And the really amazing thing about this is that it not only works quite well, but it was also very fast at that time. So we are not talking about here about gigahertz of processing power, but of megahertz. So, and you had quite large images, and still for these images it was possible to classify it at real-time capable speeds. So this specific algorithm was then also implemented in consumer-grade cameras and something like this to find the faces and something like this. So, and for getting this very fast evaluation of the sliding window approaches, 2 steps were the integral parts here. So the first thing was the integral image, which quickly enables to evaluate the Haar-like features. And the integral image, the idea is very simple, but as you will see, it's a very nice thing to evaluate this differences between regions in the end. So what it does is basically it represents the image as this integral image, and the integral images are now capturing the sum of all pixels for this pixel in this integral image. It's capturing the sum of all the intensities in this region above. So this it does for all pixels in the integral image. So that means the pixel here in this image is just having the sum over all intensities in this region. And this is the integral image. So, and what you can now do with this is that you can quickly evaluate by a constant number of operations the intensity values or the sum over the intensity values in a specific region. And this works as follows. So we are interested in getting the intensity sum in this region, and this is then given by just the 4 corner pixels of these regions, here encoded by yellow, green and blue, and the region, so the sum over the whole region is then just the blue, the green pixel, or the number in the green pixels minus the number in the yellow pixel minus the number in the blue pixel plus the red pixel, because when you think of it, so each pixel corresponds to the sum of all intensities above. You're just subtracting, when you're subtracting this area and this area, you're subtracting this 2 times here, this red area, and therefore you have to add it in the end to get then the sum over all pixels in this region. And because we can do this, the generation of the integral image only once in the beginning, this is very efficient in the end to just use 4 operations to get any region sum in the end. And the second part that I already discussed in the beginning was that you had this cascaded classifiers. So in the beginning you had very simple classifiers, which were very precise in distinguishing, okay, this is definitely not a region where a face is located, from regions where they are not so sure. And for these not so sure regions, they just pass it on to the next classifier, which is then having just more stages of the AdaBoost training trained. And by doing this for a number of cascade, you get a very quick and very precise classifier in the end that can distinguish faces from non-faces. So, but yeah, with this HAR-like features and the AdaBoost approach, you can get somehow a little bit farther, but yeah, for faces, it might work very well because we have this difference is we have locations of the eyes and locations of the mouth and so on. So, but for more complex objects, this is maybe not sufficient. And the next thing that people came up with was the so-called histogram of oriented gradients, the HOG descriptor. And the HOG descriptor enables now to capture locally the gradient information in such a way that enables the method to very accurately detect pedestrians here in this case, or persons. So here's an example of this HOG descriptor. I will also now tell you how this is combined. So the feature here, so the main ingredients are the histogram of oriented gradients, which are usually depicted like this, and the linear SVM, which is somehow a logistic regression with a specific loss function in the end. But this is not so important. So important is the generation of the feature. And this works as follows. So we have some region from the image here, here in this case this pedestrian, and we subdivide the detection window into cells. And for each of these cells, we are computing the histogram of the gradient orientations, where we are weighting the what we integrate into the histogram by the magnitude of this gradient. And this is then usually visualized by this. So each of these cells is then corresponding to some histogram. And this encoding is basically just showing you where are the main the main entries in this histogram. But this is only the visualization here. To make it really powerful now is to aggregate these cells in the end. And for this we have blocks of D by D cells, and we are, in this case we have 2 by 2. We are just taking the histograms of these cells and then put this into our feature vector. And in this specific case, we are then also normalizing the features over this whole regions by using the histograms there. And we have these overlapping regions here so that we can capture more of the shape or the shape information at the end. And we are doing this for all the regions here, and then this gives us our feature vector in the end. And by using this, we can then get a very good person detector. But this was also then applied for other objects like airplanes or something like this. So, but to mention here some additional tricks that were introduced. So to increase the number of training examples that you have in the end, they introduced this concept of data augmentation. And one simple data augmentation that you can do for pedestrians that are upright standing is basically that you flip the image. Because for the classifier, it should not make a difference if a person is facing in this direction or in this direction. So therefore you can basically double the size of the training examples that you have in the end by just flipping the images. And the other concept that they used were the concept of hard negative mining. And this is also something that you will see that it's used very often. So because when you learn the classifier or the detector in the end, you're basically interested most in the things that are just, that are hard examples in the end. Because most of the examples are very easy, especially from the negative part, because regions that are located in the in parts where not the object is are pretty easy to classify. But some regions in this negative examples are basically the very hard regions that are close to the decision boundary here. So in this case, these negative examples would be classified as person, and these are then added basically back to the training set, and then the classifier is learned again. And with this, the hope is that we having in the end for this hard examples a better decision boundary that also captures this negative examples. And when we are using this, we then get a strong classifier out in the end. And so these are basically the hallmarks of the feature engineering that we discussed now. And but an important part of this whole story is basically that this progress was mainly driven by dataset and benchmarks. So the key principle of computer vision research is that we have datasets and associated benchmarks that are driving the progress, so to say. And over time, the benchmarks were basically solved in the end, and then new benchmarks came up with makes the task more complicated in the end, but also provides new directions where you see maybe shortcomings of the current detection approaches, but also classification approaches. And this progress was furthermore a little bit incentivized by competitions. So you will, when you look back, or but also now, then you will see on conferences in a yearly basis maybe some competitions where I said, okay, from this time to this time we want to have the best performing approaches on this specific data set, and to make it a little bit more interesting, we are also giving something like a prize money. And of course the fame when you're solving this competitions, then usually this will also give you some credit in the end for solving this. So dataset and benchmarks are a key thing that drove a lot of the progress that we see in computer vision research. And one specific dataset that was very important also to drive the progress was the so-called Pascal Vision Object Classes dataset. The Pascal Object Vision dataset featured basically 20 classes shown here, ranging from airplanes to horses, but motorbikes, trains, and so on. So a very diverse set of classes. So to make also the task a little bit harder for the detectors, so that you not only have to distinguish where are pedestrians, but also have to distinguish where are different objects located in the image. And maybe in some images, there are also multiple objects located. These images, driven by the progress that the internet made over this time, were collected from Flickr. And overall, it's resulted in 11,000 images, where each image was hand-labeled by students and researchers, ensuring that the labels are quite clean in the end. And as I said, they are featuring 20 classes, and they organized annual competitions from 2006 to 2012. And together with the competition, also workshops where the researchers could discuss the current solutions or the best solutions in the end, and also see what the progress was. And the Pascal VOC challenges from 2007 to 2012 produced a data set that was very often used. So, and the special thing about the Pascal VOC challenge was that the number of training images basically was increased over time, and also therefore the complexity a little bit. And for each class it featured at least 300 images, as you can see here in this histogram. for the different classes. And for some classes, because there are more images available, but also maybe in one image is multiple person present, you have many more objects in the end. And the good thing about, or what makes the task very interesting, is that you have this mix of rigid and deformable objects. So persons that are in specific poses, but also rigid objects like airplanes or something like this. So you have to come up with some solution that basically covers both. And for the specific Pascal VOC challenge and the detection challenge, the defining method at the time was basically the deformable parts model. And the deformable parts model just used the Hoc descriptor, but now combined it with a part understanding of the objects. So in this case, we have a bicycle model here shown. So we have a root filter that basically gives some general idea about the shape of the objects. And then you have very specific part models that capture the specific parts of the objects. And then you have the deformation costs to somehow encode where could these parts be located in this case. So, and with this together, you get then a very powerful approach in the end that can also distinguish very deformable objects and can also detect maybe something like this bicycle here. And everything was driven by the Hoc descriptor in the end. And the matching process was now working as follows. So here we have this image of two pedestrians, and then we have maybe our model of a person here. So here you can see the root filters, but also the part filters. As you can already see from the Hoc descriptors, the part filters are very fine-grained. So they are capturing the shape of the object much better than the coarser root filters. And this was also then exploited in the matching process. So the root filters are evaluated on coarse images. So as shown here, you get a downsampled image, and on this you apply basically the root filter, sliding it over it, and then you get this response map in the end for the root filter. And for the individual parts, you then use these parts. So you had maybe some head part like this here. You're sliding over this, and as you can maybe see here from this visualization, you have maybe here a high response, which corresponds to this head here in this case, and the other response is this head. And then you have the right shoulder responses and so on and so on. And now combining both together, so aggregating the votes from the root filter, but also from the part filters, you then get, hopefully in the end, the real location of the objects. And the deformable parts model were basically the approach that was early on very often applied. But moving on in time, people figured out, okay, this approach of exhaustively evaluating everywhere the detector in the end is very wasteful, because a lot of the images or a lot of the parts of the images are not containing any object. They are just background. Maybe as in the beginning we saw, like you had the house fronts where maybe no object at all is located, but you're still evaluating everywhere this sliding window approach. And for this, the so-called selective search was invented. And as I said, the sliding window approach is quite efficient because we need to check and classify many irrelevant windows, and this somehow restricts us also in the kind of features that we can use to have still an approach that is manageable for the computing power in the end. And the main idea is here that we are only interested in extracting regions that are really containing some objects. So we want to have object proposals in the end. And as you can see here, this is also then combined again with the approach that the Dalal and Trix introduced, this hard negative mining, to get then a strong classifier in the end. So, but how does this object proposal generation works in the end? So, and of course, we are using fewer object proposals. We can then also use stronger features in the end. So we are not maybe restricted only to Hoc features, but we can then use more powerful features in the end. And the selective search works now as follows. It first generates a superpixel subdivision of the image, which is basically object agnostic in the end, just combining regions by the intensity. So regions here in this coarse segmentations are basically showing very similar intensity or colors in the end, or texture in the end. So, and this is the coarse segmentation. And for this coarse segmentation, we are now aggregating regions in the end. By aggregating these regions, we are then combining regions that are very similar to each other. And for these regions, we are just generate then detection bounding box, or region that we want to classify in the end. And as you can see, as the regions are very different in size, we are automatically getting also regions of different scales in the end. And when we are doing these combinations, we are then getting here this regions. So we have maybe these objects covered, but we have also maybe some background covered. But in the end, we are not producing so many proposals in the end that we can get away with much stronger features. And for the feature side, a very famous approach to then derive from these regions some features that are very powerful was the concept of back of words. So, or back of visual words in the end. So the idea of back of words comes from the document classification task. So in the natural language processing, we have a document, and we want to extract a feature for this document that captures somehow the topical content of this document. And for doing this, we are just using our dictionary, here in this case represented by this D, that just contains all words. And each word in this document then corresponds, of course, to some entry in this dictionary. And from this, we can then generate the so-called back of words, which just is a histogram of the counts, how many or how often the words appear in the text. And therefore, the name back of words makes also sense, because the structure of the whole document is basically lost, because it's just put in this histogram. So it doesn't matter where the word is in the text, but it's just the back of all the words that we find in the text. But this is usually just enough to distinguish different topics of the text. It doesn't matter where maybe computer science is in the text represented. You can then maybe by the number of how often computer science is maybe mentioned in the text, that you can then see, yeah, this text is maybe about computer science in the end. And this idea is very strong in the end, because it gives us in the end a representation of this whole thing by just a histogram. And the logical step is now to apply this similar idea to images. And this works as follows. So we are having this image. We then have some dictionary. In this case, we are having a dictionary of predefined descriptors. And how this dictionary is learned comes in the next slide. But here we are given this dictionary now. And the idea is very similar. So we're extracting again a histogram over the occurrences of this dictionary entries. And we are now extracting here regions or descriptors of the image patches, and then use just the nearest neighbor relation between the dictionary and the descriptor that we extracted at a specific position to then count this in the visual back of words. So that means we are extracting densely over the whole image the descriptors, then compare each descriptor with the dictionary, and for the closest one we are just increasing the count of the histogram entry here. And this results then maybe in this histogram. And this gives us a pretty good representation of the whole content of the image. And what is also nice is that we have now for arbitrary sized images, but also for arbitrarily sized regions, one consistent back of visual words in the end. And for the representation of these descriptors, one famous thing is to use the ZIF descriptors, for instance. But it could also be then different other descriptors. But this is not so the main importance here. So the main importance is now how to learn actually this dictionary. And for learning this dictionary, we are just extracting a large set of descriptors or image patches even from a large training set, something like this here. And then we are just using the method that we had in unsupervised learning. We are just representing this whole space by vectors, and then just use k-means or some other clustering method on top of this to then extract the cluster centers. And each of these cluster centers, or maybe nearby descriptors, that depends on the implementation, is then just one entry of the dictionary that we have in the end. So, and by using larger Ks, we can then make a very strong feature representation of the image in the end. But one thing is, in text, it's maybe not so often important where specific words are, but in image, it's specifically important where specific parts are. So it doesn't matter if something is on the bottom or the top, and so on and so on. So the next logical step was also exploited now in the selective search approach to just not compute only one bag of words for the whole image, but to subdivide the image in different parts. And then for each of the parts, we are just extracting again the bag of words approach. And this is the concept of the spatial pyramid. And we are not only doing this for 4 regions, but we can also subdivide it in more regions, like 2 by 2, 4 by 4, 8 by 8, and so on and so on. So and then we have this bag of words, and this gives us a very long representation of the image, or this part of the image, or the detection bounding box in the end. And this can then be used as a feature representation. Now coming back to selective search, especially for the Pascal walk data set, it was like that different variants of the ZIF descriptor were used. There are specific variants that also could work with color images. Here they used a bag of words with 4,000 entries and a spatial pyramid idea, and this results then in feature vectors of size 360,000, which is a pretty hefty feature vector in the end. But because we are only evaluating these feature vectors for specific parts of the image and not exhaustively for all parts of the image, this is just fine. Again, the support vector machines were quite famous at the time, so they were also applied here. And again, the idea of the hard negative mining was applied, and this led then in the end to the winning entry of the last competition in 2012, so the best performing approach. So, and when we now look at the results, it looks something like this. So here you see in this graph from this, this graph is not from the Van der Zande paper, but from the Everingham paper about Pascal walk. And this shows basically the progression of the average position from different classes. So the dashed lines are, and the solid lines are different classes. So you can see here, for instance, that the class aeroplane is basically not so complicated, which is also maybe explained because aeroplanes are usually just the only thing that happens in the image, and then it's very easy to distinguish, okay, there's something happening or not. And some more complicated classes like here the boat class, for instance, was very complicated, but also chair. But this is also maybe something that you can imagine, that a chair can have very different shapes, but is maybe also not so large an image that it can really clearly define. And here I marked just the mean average position, which is the mean over all average positions for all classes. And as you can see, over time, the researchers made a lot of progress here. But coming now to the image classification, which is just the similar task, but we now have not only a specific object, maybe in the detection bounding box, but we want to have the complete information about the whole image encoded and some label produced from this. And labels for this, as I said in the beginning, could be something like car, city, and crosswalk. So this is just a decision one has to make. Usually one of these classes is assigned, and the image classification has, of course, an application in when we want to categorize our images, but also for image search. So when you type in some search term in Google, then you want to have maybe just images of cities, and then you want to have something like this in the end. And for the Pascal VOC dataset was also used for classification tasks. And here the predominant approach was the back of visual words, as I said. So I think the most used approaches were basically the back of visual words over time. And as you can see here, the mean average position approach here, something like 0.8. So it's a little bit more progress over time here. And of course, the back of words were then combined with the spatial pyramid idea, but also multiple back of words were used. And one interesting idea is then, which was also used by the selective search approach in the end also for this task, is then the classification by detection. So that means by detecting basically the specific object that you are interested in, what you wanted to have in the end for the classification, like aeroplane or something like this, you could also use the detection output of a detector in the end. So it's just a combination of both in the end. And when we talk about classification, then we can see that here the classification task is basically approaching something where we could say, okay, this is maybe going in the direction that it's close to solved, or maybe there will not happen so much anymore. So therefore, researchers thought, okay, how can we make this task maybe more challenging or more interesting in the end? And this usually leads to the phenomenon that the data sets get larger, of course, but also more complex in the end. So and this comes to the ImageNet dataset. So here the ImageNet was motivated by the WordNet hierarchy. So the WordNet hierarchy is basically a semantic representation of terms from the English language, for instance, that represent a hierarchy, something like the mammal and placental, carnivore, canine, dog. So it goes from more general to more specific. And using these terms, the developers of the ImageNet dataset just used these terms and then used image search engines to crawl images from the internet corresponding to these terms. And of course, not all these images were maybe as perfect as nowadays. They also maybe not corresponded to something that you want to have in the end. But by this crawling, they got in the end 12 million images for this 15,000 categories, which this 15,000 categories came from the WordNet. And the specific advantage of the WordNet representation is basically that it also has basically synonyms of different terms in this, and this can be also then used to extend the search in the end. And the ImageNet categories are then verified by humans. And in this case, at the time, nowadays also more, often used these crowdsourcing services, where you just distribute a task to many different workers. And by using the power of many people that you have available, then you can also go through all the 12 million images in the end to figure out if this image is really containing the object that it was searched for. So this was basically the task of the workers. So they got present the images and should then click, like in nowadays with the captures, if this image contains the specific class. So, and together, as I said, with the data set came also a workshop and a competition. And this was the ImageNet Large-Scale Visual Recognition Challenge. And here the goal was to evaluate image classification, but also object detection algorithms at large scale. So, as you remember, we had 12 million images, and the the creators of this challenge basically decided to just use a subset with clear classes in the end, and where in the end 1,000 classes were selected from the 15,000 classes available. And this data set contains 1.2 million images for training, 50,000 images for validation, and 100,000 images, 100,000 images as hidden tested. So this is also an important thing that I talked about in the beginning, so that you want to have this hidden test set so that people cannot cheat in the end. So they had to submit their results for the test set, and they were then evaluated on the server. And I think they also restricted the number of submissions in the end. And this resulted then per class into over 700 images unto 1,300 images per class. And when people talk about the ImageNet dataset, they are usually referring to the ImageNet 1K dataset, to this specific part of the ImageNet. So when we compare the Pascal VOC to the ImageNet, then we see, of course, that because of the many more classes, you had a more fine-grained representation of the different classes. So while we had maybe in Pascal a bird, we have now very different birds represented in the ImageNet dataset, but also for cat and also for dog, and which makes it also more complicated. And for image classification now, because of the nature of the task and also the verification of the task, the people were just asked, is this specific thing that it was searched for also present in this image? And they had to just decide, okay, yeah, that's true or not. And therefore, when you look at the classes, for instance, here are some examples for the category paintbrush, then you can see that it's maybe not so clear what is the main object that is present in this image. Because when you see, for instance, here, this is in a category paintbrush, and this corresponds to this little thing here. But it could also maybe correspond to human or something like this. And the same is here for paintbrush, for this. The only paintbrush that is present is here, and the rest of the other stuff is lying around. But also here, the most dominant object is maybe the stump, but it's also here this part of the paintbrush visible. And this makes it a little bit more complicated in the end also to figure out what is the right call here. And the developers of the challenge wanted to give also the algorithms a little bit more chance to get the thing right in the end. And therefore, the targeted label might be ambiguous, and therefore they consider the top 5 predictions of each approach. And if from this top 5 predictions, one was maybe then paintbrush in this example, then this was counted as a correct classification in the end. And this is then the thing, is the targeted label under the top 5 predictions? This is the thing that people then talk about, the top 5 error rate in the end. And when we look at this data set or the specific progress that they made, then in 2010 they arrived at 28.2% of top 5 error rate. So that means they were to 82% accurate in the end, and 28% of the images were wrongly classified. And as you can see in the next edition, there was made a progress, and you can see that it's a downward trend. So, and what was applied here, so to continuing the story, they also applied something like a bag of words, but here now, a soft version of bag of words, the so-called Fisher vectors, and this resulted then in something like 1 million dimensional feature vectors in the end. And these were then used with a compression approach and to compress it and uncompress it and then to classify the images. And this was then something that led to this 25.8 error rate. So the way to handle more complex data was basically to make the features more complex in the end. And this is somehow the end of this lecture. So the thing that I wanted to focus here on was that to show that the main part of the progress was basically to figure out more complex ways to construct features in the end. And so the feature generation process, so in the end they are also learned in a way, but this learning is a little bit disconnected from the classification task in the end that we want to solve. So it's really a two-step approach. You first learn your good features, you generate this 1 million dimensional feature vectors, Fisher vectors in the end, and then you had your classifier that just used these vectors to then learn the classification task in the end. So, and with this, I come to an end, and here I summarized what we covered here. Basically, we looked at a couple of applied machine learning approach for object detection and image classification, and the main progress or the main part here was to design more complex features. So in the beginning we had very simple features which were quite powerful, but only restricted maybe to face detection in the end, or single object detection in the end. But to make it then more complex, we had the deformable part models which used the hoc descriptors in the end. We had in the selective search, but also the back-of-words approach. And this was the main deal with computer vision research, or one main part of this specific task at that time, to come up with more complex features or more diverse features in the end to solve the task. And this is basically the thing that I wanted to show here. Here are the references of the different papers. If you're interested in finding out what are the specifics maybe of the hoc computation, especially this provides a good overview of different design choices, why it makes sense to make this number of blocks in the end, and different normalization and so on. And here the Pascal Bock paper that covers also a discussion about the progress over time and what was maybe the hard parts in the Pascal Bock challenge. Then the deformable part models, back of words, going beyond back of words. This was a special pyramid idea to introduce the location of the parts basically in the back of words again, and then of course the ImageNet representation and the Fisher kernels, which are not covered here in depth because it's a little bit more complicated in the end. But here you can get more information about the Fisher kernels and the Fisher vectors in the end. The ImageNet dataset will somehow play a role after in the next parts of the lectures, when we then talk about more powerful models to solve vision tasks in the end. But next week is in here now the Pentecost week, the excursion week, where we don't have lectures. So therefore, see you in 2 weeks. Thank you for your attention.